I'm going to move fairly quickly. I want to talk about overall problems of global climate change with regard to the ocean, because there's a lot of misunderstanding, I think, about the role of the ocean in climate change. The first thing is I'm going to focus on coral reefs, because that's mainly what I work on. And coral reefs have the highest productivity, the biomass, the biodiversity, the economic value, the beauty of any marine ecosystem per unit area. And they're also, they're all beautiful, don't get me wrong. I'm not trying to compare one against the other, but corals just stand out in terms of the exceptionally high volumes they have of all of these things. For example, about a quarter of all the fish in the ocean live in coral reefs, but coral reefs occupy less than 0.1% of the ocean. So it's just hundreds of times more diverse, more productive, et cetera, et cetera. That's true by every category we know. So, but beyond that, they're our most valuable ecosystems from the point of view of the economic services they provide that we don't pay for, and therefore we don't value, because they're free goods. So we have a very serious problem. My grandfather was the inventor of macro photography. He was also the first person to take good underwater macro photographs. That's the first underwater macro photograph from 1948 in the Bahamas. But anyway, the point is just, coral reefs are exceptionally beautiful ecosystems and very lush, and you have to look at them really closely up to appreciate them. For more than 100 countries, they're the major source of biodiversity, shore protection, food supply for fisheries, and the basis of the tourism economies that basically every tropical country is trying to live off. Every country near a coral reef requires that white sand beaches that come, and every grain of white sand on a white sand beach is the remains of a living organism that lived in a reef. Okay, so that's very important to understand. They're produced by the reef and protected by the reef. Now, Robert Costanza, who was sort of the father of ecological economics, he was the first person to put together a global study of the economic value of ecosystem services worldwide. And he did that back in about the 70s or so. And then he repeated that study about 2 years ago, and he was looking at the changes in the economic value of global economic ecosystem services worldwide. And what he found is in that 20-year period, about 60% of all the economic value of losses from ecosystem services in the entire world were from the disappearance of coral reefs. Okay? So 60% of the economic losses are being borne by the people who are living in less than 0.1% of the surface area of the ocean. You can understand that those people are being impacted, 600 or 1,000 times more per capita per unit area, so to speak, than other parts of the world. So it's already a disaster for our countries, because in fact we've lost most of our corals already, and therefore we've lost most of our ecosystem services. For example, the last talk we just heard, the ecosystem services are basically proportional to the rate at which those whales are cycling that carbon. And so when you have 1/10 as many whales, in a sense, the volume of the economic services they produce are reduced proportionately. So, we've wiped out a lot of these economic services. When we go to reefs, it used to be 100% live coral that are now 10%. You can see we've lost almost everything. These are ecosystems that really are no longer functioning. They've just got a few of the remaining players still not yet dead, but they're not functioning the way that they used to at all. So the result is that coral reef countries are the first and worst affected by global climate change. And there are many causes, but this is where coral reefs are. I don't need to delay on that. But almost every place I go, I've been diving, since I could walk in coral reefs. Almost every place I go has far more dead corals than live corals. There's very few places that are healthy anymore. Originally, we did it by what I call local activities, throwing anchors, dredging, stepping on corals, physical activities, that sort of thing, in the water itself. Well, those you can control by setting up marine parks. Don't step on corals, don't dredge, don't, so forth. In principle, you can control those. But then, until about the 1950s or 60s, those are the main threats to coral reefs. After that, we began seeing what I call regional threats. Threats that were not caused by activities in the water, they're caused by activities with people on land doing other things. Cutting down the rainforest to plant crops, letting the soil wash into the sea, not treating the sewage, letting the animal waste flow into the ocean, that sort of thing. So those are regional threats that come from totally unrelated activities that don't even take place in the water, but they affect everything downstream and down current from those areas. until, in the 60s, that began to be a major threat, what I call regional threats. But then in the 80s, we began seeing global threats. And this is where we began seeing whole reefs thousands of kilometers long turning white, bleaching, dying, for reasons we had no idea why. And these are areas that had no local stresses. There was not a source of pollution. Some of these places were places no one had ever died before, and they were being affected. And since the 80s, the major killer of corals has been global warming and new diseases, which are another plague. I mean, we never used to see diseases in the old days. Now we see them in almost every reef we go to. So the result is we've already lost most of the corals in the world, far and away. I mean, we have, there's a few dead reefs remaining that are slowly crumbling as they fall apart, and so we've lost those economic services. This is the first photograph of coral bleaching in 1963. We never saw, this wasn't caused by high temperature, this is caused by hurricane runoff. So bleaching, corals can't run away from stress. All they can do is turn pale or die. And they bleach in response to almost any stress. But in fact, almost all of those are local stresses, and you know why it happened. A coral in a tide pool that's exposed at low tide in the middle of the day, and the water is very hot, stuff like that. A coral right downstream from a river mouth swollen by a hurricane. But before the 80s, all the bleaching we saw was local. It had an obvious local source. Since the 80s, almost all the bleaching we have seen is caused by global warming, by high temperatures. It took us a long time to figure that out, but I basically put together the NOAA satellite sea surface temperature database from all the satellites that went up. It went up in 1983. We began measuring global sea surface temperatures worldwide. So I put that database together. What I found was we could predict coral bleaching accurately from satellite data alone, simply by mapping out the areas of the ocean that go 1 degree C above the average temperature for the warmest month in the warm season. 1 degree causes mass warming above the normal average temperature for that month, causes large-scale bleaching of corals, but not mortality. 2 degrees above for 1 month causes large-scale mortality, or 1 degree above for 2 months. So just in round numbers, coral reefs can't take any more warming. I mean, before the 80s, we never saw thermal stress in reefs. Now we see it every single year, without fail, someplace or another in the world. So, I mean, it's bizarre to imagine that we were so close to the upper limit of corals for so long and never hit it until the 80s. But since then, we hit it practically every year. And it's getting worse and worse. And we know exactly when and where it'll happen, because since 1990, I've been able to predict when and where bleaching will happen from satellite data accurately before you can see it in the field. Can warn people beforehand the conditions are such that you can expect bleaching. I thought that once it was shown that temperature was clearly the cause of bleaching, the world would do the right thing. But of course, what they did is they denied it could be due to temperature, and the governments of the US and Australia and other countries spent millions of dollars denying that temperature could be the cause of bleaching, and spending millions of dollars trying to prove that it was anything else. Anything else. So, there are all sorts of improbable explanations, of which the most popular one now is ocean acidification, which is a real red herring as far as coral reefs are concerned. It's an interesting one. Ocean acidification is a serious problem for cold waters and deep waters. For small things that live in cold waters, like larval oysters in the Pacific Northwest, they're dying as larvae in the water. The larval skeletons dissolve before they can settle. So they're not making it. But it's not for coral reefs, because I'll show you later on, the tropics releases CO2 to the atmosphere. It doesn't absorb it. The tropics are going to be the last place that are going to be affected by acidification. The very last place. Okay? But they're already at their temperature limit. Now, every time I see an article about ocean acidification, they show a picture of corals that have been bleached by high temperatures. That's what they show. But in fact, acidification is the only threat that doesn't cause bleaching of corals. You can throw a coral in an acid bath, dissolve the skeleton completely, and you don't harm the coral at all. It doesn't even bleach. It completely retains its color. Okay? And you can then keep it in acid water for a year or two, as long as you give it food, and then put it back in normal seawater, and it'll grow a new skeleton again. So in fact, acidification is not an existential threat to coral reefs at all. What it will do is, if we let them die from high temperatures, which are right already at the edge of doing, then acidification is going to kill their dead skeletons in 50 or 100 years, dissolve them away slowly. But it's not going to kill the corals. And the reason it's a really dangerous red herring is because if we try to focus on stopping CO2 in time to prevent acidification, we're going to guarantee that we kill all the reefs from global warming. because we're just a couple years away from that. On the other hand, if we control CO2 in time to stop high temperatures killing corals, then we solve the acidification problem automatically and trivially. Okay, so but it's a real mistake to focus on acidification as a threat to reefs because it's so far down the list it doesn't even count. What's killing corals now are high temperatures. Okay? Pollution, new diseases, other things, but high temperatures is by far and away the biggest one. Okay, for example, I mean, this year I've been spending quite a bit of time in Indonesia. I've been dived in reefs that last year I dived in that were 100% live coral cover, some of the most beautiful and perfect reefs left in the world. This year when I went back, somewhere between 95 and 99% of those corals had died from heat stroke in the space of a couple weeks earlier this year. Yeah, I mean, we hear a lot about the Great Barrier Reef, but in fact, it's happening all over the world, and no one's reporting it anymore. The dive shops refuse to report bleaching because they think it's bad for business. They're actually concealing it. It's almost impossible to get the data. Well, we know from the temperature maps when and where it's happening pretty accurately, even so. Anyway, but you know, it's shocking to me to see because I do a lot of my work in Indonesia, which is the country with the largest area of coral reefs in the world and by far the highest marine biodiversity, far and away above any other part of the world. And a lot of the richest reefs in Indonesia were essentially wiped out this year by high temperatures. Next year is going to be worse, almost certainly. So, okay, so we've been able to predict coral bleaching accurately, and as I say, we're seeing in some reefs that I dive in, 99% or more of the corals dying from high temperature. And these are in places that far or near humans. I mean, this is an example of a recent hotspot map. The areas that are in yellow are areas that are too hot for corals. We're getting no reports here from the Central Pacific, but in fact, most of the corals there must have died in the last month or two. It's been that hot for that long. So these hot patches move around, and there's a very interesting pattern to them with global warming. Now, what I did, if you ask a physical oceanographer, is ocean circulation changing? Their answer will be, well, gee, we don't have enough data. We need a couple $1 million and another 20 or 30 years of data, and then we can tell you if ocean circulation is changing. It's based on measurements of the physical currents, okay? What we did, and this was years ago, is we simply analyzed the sea surface temperature changes. The sea surface temperature changes are only the top millimeter of seawater. Okay? It's not measuring the deeper stuff. This is only the surface. But in mapping this, the areas that I've marked out in yellow here are the areas that are warming more rapidly than average worldwide. Okay, that are in yellow. And blue are less rapid. And I've marked out in red spots, the centers of some of these areas are warming more rapidly than average. And what you actually will see is there is a pattern. All these semi-enclosed seas, the Red Sea, the Caribbean, a lot of seas that are semi-enclosed are warming up more rapidly than average. All the really warm currents of the world are warming up more rapidly than average because more heat's flowing out of the tropics. All of the cold currents are warming up more rapidly than average. Okay? All of the upwelling zones of the world, where that deep cold water comes up and causes huge phytoplankton blooms that lead to the whales, okay? All of those areas are warming more rapidly than average. Now, we're used to blaming overfishing for destroying the fisheries, and it's absolutely true. But at the same time, the most productive parts of the ocean are collapsing from the bottom up, that we're destroying them from the top down. It's collapsing from the bottom up because the surface water is getting so warm. The cold, nutrient-rich water no longer reaches to the surface anymore, and so we no longer are having the big phytoplankton blooms. And we're seeing upwelling zones gradually shutting off simply because the amount of warm floating water on the top is too great. So it's a very serious impact. And global warming, the areas, here, this includes most of the areas of coral reefs and areas that are warming more rapidly than average. Now, the reason there's variation is kind of an interesting story, as you'll see a little later here. These are the areas that are warming up more rapidly than average, so it's affecting fisheries already in ways that are not included in the models because we're focused on overfishing rather than bottom-up collapse, but both are happening. The areas that are warming up more slowly than average are kind of marked with black dots. There's one here in Indonesia too. And these areas are also interesting because as global warming proceeds, some areas heat up more quickly than others, especially over land, and that causes changes in the atmospheric pressure distribution. And that's what drives the winds, is a pressure difference between points. And so as the pressure distribution varies, so do the wind speeds. Now, it's been happening worldwide over the last 4 or 5 decades or so, is that wind speeds have actually been decreasing over most of the ocean. quite significantly in many areas. And in those areas, those are the areas that are warming up more rapidly than average. Okay, the areas that are warming up more slowly than average, I've marked here in blue and black, are the areas where wind speed is increasing. That's a minority of the ocean, slowing down over most of the ocean, increasing in a small minority of it. And what that means is the areas warming up more quickly than average, the phytoplankton productivity is collapsing because the nutrients aren't getting up to the surface anymore. These areas all around Antarctica and the southeast of the Pacific, Indian Ocean, Atlantic, and the northeast Atlantic, off of Greenland and so forth, those areas the wind speed has really picked up. And that means there's a lot more wave mixing in those areas. And that means as the surface water is swept away, cold water is being drawn up to replace them. And that's preventing those areas from heating up as rapidly, is the increased wind speed. And those areas, because of the increased wind speed, actually have higher phytoplankton productivity. So they're exceptions. But they're mostly in areas around Antarctica or in the oceanic deserts of the world with a very low productivity. But the point is, we're seeing ocean circulation change in every part of the world. And that's not included in the climate models, because the climate models can't match atmospheric phenomena to marine phenomena very well because they operate on completely different timescales. Okay, it takes 1 year to mix the atmosphere. If I put CO2 in one hemisphere, it'll be all over the atmosphere a year later. It takes 1,600 years to mix the ocean. The timescales are completely different. You can't model them with the same equations very easily. So people usually ignore changes in the ocean when they have climate models. But in fact, the impacts are going to be very large. Because in fact, as you can see here, circulation is changing everywhere for one reason or another. So, and a lot of that's linked to wind speed. Now, here's why it's much worse than people realize. This is in my island, home island in Jamaica. And this is the ancient sea level from 130,000 years ago, which is the last time when global temperatures were 2 degrees C warmer than today. And that's that ancient sea level. You can see it cut into the cliff, fossil corals below. And here's the modern sea level, which is about 7 or 8 meters lower than today's sea level. Okay? There's a fossil reef in front of here, where the bottom corals are all in position of growth, and the top ones are all smashed and lying on their sides. In fact, probably most of them died from high temperatures all around the equator of the world at that time. But now, the thing that's important here is at that time when it was about 2 degrees C warmer than today, when sea levels were 7 or 8 meters higher than they are today, when there were crocodiles and hippopotamuses in London, England, you can see them at the British Museum of Natural History. Okay, at that time, CO2 in the atmosphere was only about 270 parts per million. Okay? Here now, here's today's sea level where we have 400 parts per million. Here's where it was when it was 270 parts per million. That's because we haven't yet come into equilibrium with the 400 ppm. When we do, sea level is going to be way up the cliff. Okay? So, and that's why I mentioned the time scale. Here is the last 800,000 years of CO2 from the Antarctic ice cores, and this is the time that fossil sea level formed, 130,000 years ago, when we were only 270 parts per million CO2. Now we're at 400. We have not yet felt the response to the 400 ppm. We have not felt that response yet at all. Okay, this is the last 12,000 years of global temperature. It's been nice and stable for 12,000 years. That's a world, you know, we've evolved in and come to be used to. And this are IPCC projections about what is going to happen. And as I'm going to show you, there's serious underestimates of what is really going to happen. Okay, but that's the IPCC projection. Now, the problem with IPCC is that IPCC was mandated by the United Nations, by the governments of the world, to provide model-based predictions on what will happen with global warming in 5, 10, 20 years, maybe 100 years from now. Okay? They didn't care what happened after 100 years, because that's not their fault. Okay, but the fact is it takes 1,600 years for the ocean to mix. And until the deep sea warms up, we won't feel the warming at the surface. Okay, there's a built-in time lag of thousands of years. If we increase CO2 in the atmosphere, we won't feel the full temperature effect for several thousand years. And so, in fact, this shows burning all the fossil fuels in the next 100 years. This is the CO2 infrared crashes because we run out of coal and oil to burn. That's the theory. But at that point, as you can see here, CO2 goes up. we stop producing CO2 in the atmosphere, it stays high. It's going to stay high for hundreds of thousands of years. Okay? And temperature, this is after 100 years that we burn the CO2, the temperature goes up, and again, that's going to stay high. It's still increasing here 1,000 years later. Okay? And then this shows the expansion of sea level due to the expansion of water. As it gets warmer, it expands. And then here's the increase in sea level from the ice caps. Okay, 1,500 years later or so, sea level's still rising. Okay, because it takes about, maybe 5,000 years or so for the ice caps to melt and flow into the sea, although for sure it won't be a continuous slow process. It'll be lubricated suddenly and slide in large amounts. That'll be unpredictable. But the point is that, and those effects there won't come down for millions of years. The last time, in fact, we had a CO2 temperature crisis in the world, this is long before the ice ages, corals went extinct for anywhere from 4 to 20 million years. Okay, so what we've set in motion now, even if we never burn another gram of coal or oil starting this second, it was set in motion, climate change is going to last for millions of years. And they're ignored by the IPCC projections because they stop after 5, 10, 20 years, or 100 years, and they ignore all of this. So in other words, they were given the wrong homework assignment. They were asked to answer the wrong question. They were not asked what is the impact going to be on climate that we need to prepare for future generations. It's what can the politicians get away with not being blamed for? And they were given a totally fictitious time horizon for their models that bore no relationship to the fundamental processes that we need to understand. And so it's really a disaster in that sense. So people have been lulled into a really false sense of security. Now, to come back to the changes, well, the IPCC models are only the short-term ones. But if we look back at the actual long-term climate record, what it shows, and like that photograph I showed you from Jamaica, I'll show you here. This shows the last 800,000 years or so of global temperature and CO2 from the Antarctic ice cores and sea level versus temperature from the Antarctic ice cores. Here's today's temperature. Okay, it's about equivalent to about 260, 270 parts per million pre-industrial CO2 because we haven't yet felt the response to the excess. But here's where the extrapolated data for the last million years of the Antarctic ice cores say we should be for 400 ppm, which is about 17 degrees C warmer than today. Okay? And here's where sea level should be for 400 ppm. That's 23 meters or 75 feet higher than today. And that's for today's level of CO2. Right now, what we have right now. That's what we have to expect. And no government is prepared for that because they're dealing with IPCC projections. Oh, it's going to warm half a degree and sea level will go up 10 centimeters. That's what they're talking about. They don't have a clue how serious it is. So from these data, we can also say what is a safe level of CO2. And if by safe level we mean what we've been used to for the last 12,000 years, well, then I would argue that the safe level of CO2 is about 270 parts per million, or pre-industrial, maybe 260 parts per million, because 270 was 8 meters higher than it is now. Okay? So, there's some fluctuations due to the orbit and so forth. But anyhow, the point is, we're basically 40% too high in CO2 already, and if we don't reduce it by about 40%, we're going to see these consequences in future generations. Not in our lifetime, but they will happen. So we have a real mess we need to clean up. So emissions reductions cannot do anything to remove the excess of CO2 in the atmosphere. It'll just slow the rate of increase from this to this. Okay, what we need to do is we need to bring CO2 down, and that means we've got to focus on the sinks. And the climate change negotiations focus only on emissions. Sinks are not included because honest carbon accounting was never included in the UNFCCC by design. It was deliberately cut out at the very beginning. So we don't have any honest accounting of sources and sinks of greenhouse gases. And so therefore, and this is where the real problem is, as I'll show you, soils on land are the only place we can really hope to store the carbon in time to prevent the worst damage. And soils are not included in the Climate Change Convention, nor is environmental restoration. These words are not even mentioned in the Climate Change Treaty. Okay? So it's a really serious problem. Now, so let me go back to this. We call this geotherapy, which is restoration of the natural mechanisms by which ecosystem services regulate our climate, our temperature, our water supplies, our productivity of our lands and oceans, and everything else. So we're really calling for restoring the natural mechanisms that regulate our life support systems. And in fact, if we don't restore those natural mechanisms, there's no way to stabilize CO2 at safe levels. I mean, all the stuff about carbon capture and sequestration is hogwash, about pumping CO2 into holes in the ground. We know what that causes. That causes earthquakes. I mean, you just ask anyone in Oklahoma. You know, it doesn't work. And worse, it prevents this carbon from being recycled into biological reuse, which is what we need. We need to increase recycling instead of preventing it, which is what these people are proposing to do by pumping CO2 into holes in the ground out of fossil fuel plants, which, as I say, won't it won't reduce CO2 below today's level, even if you do it all. Now, if we look at the global carbon cycle, originally there were kind of two major components: the land cycle, photosynthesis, decomposition, respiration above and decomposition below, and that was pretty much in balance until we started cutting down the trees. And in the last 10,000 years, we'll put about half the excess CO2 into the atmosphere from deforestation and land degradation. About half of the excess we've done over 10,000 years. The other half we'll put in less than about 100 years from fossil fuels. Okay? It tells you how much faster that is. So this is the fossil fuel component here. Okay? It's thrown the whole system out of balance. And then there's the ocean cycle. The ocean cycle, again, there's a lot of CO2 going in and out. And a lot of people say, oh, well, all we need to do is pump CO2 into the ocean. Okay? In fact, I mean, there was one crazy proposal by a very famous scientist who proposed dumping a bunch of nuclear reactors into the North Atlantic and letting them blow up, with the idea that that would make the ocean boil and turn the whole ocean over and mix CO2 in. Really, this got published in Nature. I'm not kidding. Okay? I'm not kidding. It would have taken all the excess CO2 that's in the deep ocean, put it into the atmosphere. That's another story that they weren't aware of, but actually this was seriously proposed by Jim Lovelock, no less. He got this published in Nature, proposing to sink nuclear reactors and boil the ocean. Okay? Well, that's an example of what we call geoengineering. It's the opposite of geotherapy in every possible way. Okay, now the problem with the oceans is very simple. There's a lot of CO2 going back and forth, but that's controlled by the winds and the waves. And we affect them, but we can't control them. We can't control the wind speed. You ask any sailor, you know, you can't control the wind speed. So there's stuff bouncing back and forth, but the oceans operate in a very different way, and some of the talks we've heard, you know, in the last couple of days have referred to that. The first thing is that if we took a look at the total amount of carbon, there's about as much carbon in the biomass on land as there is CO2 in the atmosphere. Okay? Roughly about the same amount. The amount of the biosphere in the ocean is about 200 times less. Okay, all those whales, even when there were a lot of whales, don't add up to a lot. Okay, and the reason is that the fundamental differences on land, the plants have had to evolve to avoid the fungi. So they had to evolve forms of carbon that were resistant to degradation, otherwise they couldn't stand up, they'd just be eaten on the spot. Okay? And so they developed lignin, and that's led to, you know, forms of soil organic carbon like biochar that essentially lasts forever in the soil. And so there's 5 times more carbon in the soil than there is in the biosphere or in the atmosphere. 5 times more, but it's not included in the Climate Change Convention. So the point is here is that we can't possibly store more biomass in the ocean that would make a difference. Here, if on the other hand, we're removing 120 billion tons of carbon every year in photosynthesis. If 1/10 of that was converted to biochar and put into the soil where it doesn't break down, we could be drawing down the excess CO2, you know, in the time scale of about 50 or 60 years. Okay? Now, the ocean will degas CO2, but the ocean is going to turn over in a time scale of thousands of years. So what comes out of the ocean really doesn't matter. The land is the only place we can do it. The thing about the ocean is there's only one way to turn the ocean into an effective carbon sink, and that's to kill it. You're doing a pretty good job. What you do is you turn the whole ocean into a dead zone. Okay? No oxygen. The organic matter piles up in the bottom and doesn't decompose. And that's happened several times in the geological past. In fact, every time we've had a super greenhouse, super CO2 greenhouse, and that's happened, you know, 4 or 5 times in the geological past. The reefs died, everything died, and the oceans got filled with black slime. organic rich slime because there was no oxygen in the water. It was too hot for oxygen to be in the water. And so to turn the ocean into a carbon sink means killing it, okay? And we're doing that on a local scale, but we're not doing it nearly fast enough to make a difference, because that again, with the ocean, I don't show the long-term change. The rapid exchanges here is that when a tree draws CO2, it'll hold the carbon for maybe 100 years before it dies. When an algae takes up CO2 in the ocean, it makes a little tiny cell, maybe 10, 50 microns across, that gets eaten by viruses and eaten by zooplankton, turned back into CO2 within days. So all this comes right back. It doesn't go down. The only way to make it go down, be stored, is to kill the ocean. So the ocean is not at all a possible solution to this. And people who are proposing fertilizing the ocean to get rid of CO2 really don't seem to understand what they're talking about. Anyway, if you do that near coral reefs, you're going to cause massive harmful algae blooms, and that's killed our reefs near all populated areas too. So the key thing we've got to understand about the ocean is the deep ocean holds about 95% of the heat in the system. And not the ice caps, not the vegetation, not the atmosphere, not anything else, not the rocks. It's the deep ocean. And the deep ocean has been chilled down to just above freezing, because for the last couple million years, during the ice ages, the ice caps have chilled the oceans at the poles, and that's gone down to fill up the whole deep sea. Until we warm up the deep sea, we won't feel the full effect at the surface, and so therefore there's a couple thousand years of time lag. And that's why it's much worse than people realize. And of course, there are variations from place to place, because the red is the surface currents, the blue are the deep ocean currents, and so that determines where the CO2 comes up, and that's why it's particularly bad up here, because a lot of the CO2 on the bottom, with all the decomposition of organic matter falling, comes back up here, and that's why that's so acidic. This area, the eastern Atlantic's also really acidic as well. So I don't want to get into that. This is solubility of CO2 and oxygen as a function of temperature. The warmer it gets, the less oxygen and CO2 is in the atmosphere. So if we go into a large global warming scenario, we go into an anoxic situation much more easily. Any place with restricted circulation will go anoxic. And at the same time, we'll degas a lot of CO2 out of the atmosphere. And that's already happening in the tropics. I mean, the tropics are so warm that CO2 is coming out of the atmosphere. It's not going out of the ocean to the atmosphere. It's not going down the other way. Okay, well, as I say, the oceans are built upside down. There's just a lot of, in aquatic ecosystems, a lot of big fish and a tiny little amount of algae. In the land, it's exactly the opposite. So the oceans just don't serve as an effective carbon sink. They're the first victims of climate change. They're not the solutions. If we look at net primary productivity worldwide, you can see how the land dominates over the ocean. The land has a possibility of storing and sequestering very much more carbon. So what we need to do is, I think the key point is that the claims that the ocean can be a carbon sink, in my view, are accounting errors of people taken gross fluxes and ignored the net fluxes. They've ignored the fact that it all comes right back at you. And so we can only really do that by killing the ocean. So this is what we need to do, is take the dangerous excess of CO2, 140 ppm, out of the atmosphere, store it in vegetation, and then put it in soil where it'll stay forever. That's much more effective. Now, this is soil organic carbon. We've written a book on methods for increasing soil organic carbon. I don't know if we'll talk about that here. But the key point is that, a couple things, is that this is terra preta in the Amazon. These are the black soils of the Amazon that are 10 to 40% carbon, because the Indians worked out in ancient times how to turn the poorest soils in the world into the most fertile by adding carbon. Carbon's not a fertilizer, but it holds on to the nutrients from the water, so it means you can restore the fertility of the soil. When we add rock powders, and this is some work I did in Panama, rock powders alone increase the growth of trees many times because it's providing all the elements that plants need. That's not in the biochar. You've got to add the rock powder to the biochar and the other missing elements. But if you pay attention to soil fertility, we can, in fact, greatly increase the fertility of almost any area. And when we do that, there are other climate benefits. This shows air and soil temperatures in the Amazon, in an undisturbed jungle, and the areas about 100 meters away that were clear-cut. Temperatures got about 10, 12 degrees warmer in the same. It's not due to rainfall. It's just simply due to the loss of evapotranspiration cooling. The plants are sucking water out of the ground. They're sucking heat out of the upper canopy and putting it into the atmosphere, increasing ocean circulation and rain. But that's a cooling mechanism. And when we cut down the forest, we lose the natural cooling mechanism. So we need to restore that as well. And in doing so, we'll restore the water cycle to hold the water in the soil where we need it. So as I say here, once again, I mean, almost all this water that goes into the atmosphere, 95% of that goes through trees. It's not ordinary evaporation. And so we've lost a lot of this recycling of land. Like the fact we've removed half the biomass that's been destroyed, half the carbon in soils that we've converted has been lost. So this natural cycle of rain on land is being destroyed. But if we replant, we can regenerate that and prevent the runoff into the ocean. So large-scale environmental restoration is the only way to do it, and the techniques are well known. The problem is governments are not doing that. I'm going to talk about this a little bit more tomorrow because I want to show you how we restore these marine ecosystems on a large scale. We have the methods to do that. I don't have time to talk about that now. I'll talk about that tomorrow. But I mean, it is also crucial that we put pressure on the United Nations Framework Convention on Climate Change to include environmental restoration and soils and honest carbon accounting as part of the treaty, because if we don't have honest accounting, we can't turn an unbalanced carbon cycle like this into what we need, which is putting more carbon into the ground and stabilizing our climate at safe levels. And in particular, we need to do this in the marine wetlands, because half of soil carbon is in wetlands and swamps. Half of that is in coastal wetlands, mangroves, salt marshes, and seagrasses. So the salt marshes, the seagrass, and mangroves hold more carbon in their soil than the atmosphere has. And that's in less than 1% of the area of the ocean. So if we restore, and we're losing those, we're losing the oyster reefs, we're losing the mangroves, we're losing the salt marshes, almost as fast as we're losing coral reefs. But if we restore those and restore the incredible amounts of carbon they're able to hold, 10, 20, 40% sometimes, just like terra preta, that'll be the biggest bang for the buck we can get for restoring environments, restoring ecosystem services like shore protection, fisheries habitats, and at the same time, storing carbon on a very large scale. So that's what we need to do, and my conclusion is marine ecosystems are the first victims, but to save the oceans, we have to save the land first. Thank you.